Hello, everybody. My name is Panagiotis Kassanos from Imperial College London, and I will be co-chairing this session, today's session, day 2 of our workshop with Professor Kaspar Althofer from Queen Mary University. For those of you that were not with us yesterday, in day 1 of the workshop, the session yesterday focused more on the general topic of soft robotics, actuation, implementation, and clinical translation. We heard some very interesting talks about snake-like endoluminal soft robots, also about embedded sensing using fiber ratings and artificial intelligence, machine learning approaches for the sensing data. We also listened to hybrid approaches for soft surgical robots, combining also rigid parts as a means of exploiting the advantages of both approaches. And we finally listened to the clinical perspective on soft surgical robotics and the evolution of endoluminal interventions and surgical robotics and the challenges for the next generation of technologies. What was common in all of these talks and what was clear was the need for sensing. How do we embed sensing in these surgical soft robots? And this will be the focus of today's session. What we need is sensors that can be used to for motion control and also to sense the forces applied to tissue, but also methods to analyze biofluids and tissues in situ that can help in clinical decision support during interventions. So that's the focus of today's session. And we have 4 excellent speakers, starting with Professor Robin Dahia from the University of Glasgow, moving on to Dr. Benjamin T from Singapore, and also Professor Carmel Majidi from Carnegie Mellon University, and finally with Sheila Russo from Boston. The workshop also continues tomorrow, focusing more on the modeling, learning, and control aspects related with soft robotics. Unfortunately, if you want to join tomorrow's session, you will need a separate registration. So please use the Eventbrite registration to register for tomorrow's session as well. I will also like to highlight that together with all these talks, we have a virtual poster session that's online in our website. So please visit and have a look at the posters prepared. And 9 out of 10 also the posters are also accompanied by videos. So please have a look at those at your own time. And with no further delay, I would like to introduce Professor Ravinder Dahia. Professor Dahia, he is a professor of electronics and nanoengineering at the University of Glasgow, and he leads the Bendable Electronics and Sensing Technologies Research Group. He's a fellow of the IEEE and president-elect of the IEEE Sensors Council, and a distinguished lecturer of the IEEE Sensors Council. Thank you for being with us, and the floor is yours.
Oh, well, thank you very much, Panos and Kaspar. Thank you for inviting me. Can you hear me well?
Yes.
Very well.
Okay, thank you. All right. Can you confirm if you can see my screen?
Yep. Yep.
Okay, so thank you very much again for inviting me. And the title of my talk is Soft Electronic Skin. A very brief introduction, just 1 slide introduction about what we do here in Glasgow. In my group, we try to understand the sense of touch in humans and then develop the technologies for a large area electronic skin for robotics and prosthetic applications. And some of these technology that has been developed is also then comes back in the form of wearables, etc. And that closes the loop. So in that sense, learning from humans, taking it to humanoids and bringing it back. That summarizes as in the research in my group. Here is the outline of my talk. So I'll spend a couple of minutes describing why electronic skin is important, generally in robotics as well as medical robotics in particular. And then taking you to the second part of my presentation, quickly taking you some examples of solutions available in the midterm, in the near term, then taking it to midterm and long term. And then I'll conclude this talk. I normally include this today's. I don't lecture. I don't have much time, so I would be skipping the second part, which is flexible electronics going towards human side. Okay, coming to the first part, I would like you to visualize, imagine this type of experiment. You're doing this experiment, put your hand on the ice block for some time and try to grasp an object nearby. Very likely you will fail to grasp the object, and object will slip out of hand and you are not able to do anything, because for that moment, for a temporarily the sense of touch is lost. And this highlights the importance of sense of touch in humans. And the important question then arises is, why do we develop prosthetic limbs or robotics then without sense of touch, if it is so important? It is also important in case of industry. If you have been to automation, robots working in cages, as you see here, and no human is allowed to work to enter in these cages. And by chance, if they enter, then you also come across news such as this one. Robot kills man in Volkswagen plant. So even if the mistake or error by the human worker who entered into the workspace of the robot, robot should have been able to stop, and human robot interaction in that case should have been much safer. So that also highlights, because that requires physical contact as well, and maybe in some cases soft contact or proximity detection. This highlights also the importance of electronic skin or distributed sensing all over the body. This is also needed in case of future robotics, as we see robotics evolving rapidly, and we have seen robots in one way or other entering in our daily life. And when we talk about Industry 4, then role of a robot becomes very important, not just as a machine, but also as a co-worker. And if that is the case, and as a co-worker, there will be a lot of opportunities for human and robot to have a physical contact. To maintain that safety of contact, it's important to have electronic skin again. There are several other areas on this slide. As you can see, there are some push factors, such as in the case of medical applications, you have the haptically driven robots and getting the tactile feedback to the surgeon, or a minimally invasive surgery with tactile feedback, allowing a surgeon to palpate the tissues inside the body, to some of the futuristic pull factors, for example, providing sense of touch or haptic feedback in case of your smartphones or tablets, etc., allowing a doctor remotely to palpate the patients, as well as taking it to retail sector and the human or brain controlled soft robotic limbs with sensors all over. So these are some futuristic examples, and at the center remains the question, what makes different surfaces feel differently, etc. These are the scientific questions we have to address while developing the technology. Coming back to the technology, in order to develop effective tactile skin or electronic skin, there are several things that one has to look into. And these are either in terms of functionalities or in terms of hardware or manufacturing. When it comes to hardware, you have to look at mechanical aspect and the electronics or electrical aspect. Sorry, I need to switch back. Okay, can you see my full screen?
Yep.
Okay, thank you. So you need to look at the mechanical as well as electrical aspects. So when it comes to mechanical aspect, flexibility, conformability, stretchability, etc., they are very important. And in case of electronics, one has to look at the fast response, distributed electronics. One has to look at limited communication. So that connects to large amount of data that you are collecting from all over body. And then you have to take care of look at the system side as well. Even if you take care of all these aspects, there are still issues that you have to deal with in terms of manufacturing, such as, is it the solution we are developing is manufacturable or not? Is it easy maintenance? Is it low cost? Is it reliable enough, etc.? So these are various aspects one has to look into. And then the other aspect is that sensors are distributed all over the body, and there are multiple type of sensors, not just one, which allow us to feel objects as a hot object or cold object, or or a soft or a hard object, or a brittle surface or a smooth surface, etc. So these all require different type of sensors. Sometimes there's a multimodal interaction. Sometimes it's a single sensory modality that is needed. And this is distributed all over. Distributed of electronic skin or tactile sensing all over the body has been considered as one of the challenges when we talk about implementation. And that challenge comes because large number of sensors are to be placed with different sensitivities from different body parts. So some places there are high resolution, other places there is low resolution, etc. Then you have to look at the electronic distributed electronics. Currently, if you look at electronics, it is largely planar, and it's the chip size. So the distribution of large area still remains a challenge because you have to have uniform response of electronic or transistors. Then you have to look at distributed energy. Nobody has thought about distributed energy. We see robotics design, which is all backpack, batteries, etc. Whereas skin, if you look at human skin, it's all distributed biofuel cells, etc. And they basically drive the sensors and actuators or muscles inside the body. So these are various aspects. Data I have not counted now, and communication, etc. All these make electronic skin interesting as well as a challenging topic. With this background, I'll take you to some of the solutions, what can be done in, let's say, near term, some solutions which were implemented as a part of, as an example, RoboSkin project, where IIT, Italian Institute of Technology, led that project. And one of the interesting aspects of this project was that it used the off-the-shelf components, rigid components, off-the-shelf components on flexible printed circuit boards. They were integrated on the back side of the printed circuit boards. On the left-hand side is a humanoid robot iCub without skin. This is the skin without package, and you can see here a packaged version of the skin. And the interesting aspect of this approach was that it used triangulation technique. Now, triangulation technique, those who are familiar with computer imaging, triangulation technique is used for 3D imaging. And that knowledge was brought here into hardware, and that's an interesting aspect here. It's interesting because this particular simple fact allows you to develop a generic solution which can be implemented on any type of robot. From the electronics viewpoint, this is also very challenging because most of the electronic equipment that we have got, they are good to realize electronics on planar substrate because they rely on techniques such as photolithography and light travels in straight lines. So you are able to realize on planar surface very well controlled dimensions, but not otherwise. So in this case, coming back to this Fuller map concept, so if you take a spherical surface and you take triangular projections, and you make a 2D layout. Once you go 2D layout, if your skin is also made of triangle, you are expected to cover, you can expect to cover maximum area, and then you can rebuild the whole surface again. So in that regard, if you take an example of iCub again, you got the 3D map of iCub, make a 2D map, put the sensors wherever, maximum area, cover the maximum area, and then rebuild again. In terms of electronic skin, you can see all triangular patches here. There are 12 electrodes here. It was a capacitive sensor. And on the back side, there was a capacitance to digital converter chip, which is available off the shelf. Between triangles, you can see these small dots here. These are essentially the connections between triangles. So that led to each triangle, a 16 triangle making one patch. And then you have communication at microcontroller and communication through I2C communication taking place. So the capacitor, the top side was covered with, in this case, was covered with a soft elastomer. And when you press the soft elastomer, the electrode, the top layer was grounded. It was a conductive fabric. And then when you press them, they come closer and capacitance would change. That is used here to detect the contact point as well as to contact force. That was one example. But in this example, the bottleneck in this example is that you are able to use off-the-shelf component, but because of the rigid components that are being used, the bendability is not high. So if you go back to this image, you can see skin is mostly on the areas of body parts with large curvature. Whereas in case of medical applications or other, let's say medical application only, you have surgical instruments such as minimal invasive surgery, where you are entering the tool through a small hole, and the curvature is really small, and you need to have new solutions. You need to develop new solutions to get the tactile image from inside the body, or to allow clinicians to palpate the tissues inside the body. To that extent, one has to look into new electronics, new solutions. These solutions should lead to high performance electronics. So there are many examples of organic electronics or organic semiconductor based transistors, but the performance or in terms of transistor switching frequency is not as comparable to this monocrystalline silicon or the conventional electronics that we come across. That leads to fast computation and fast communication. So in that regard, our approach has been that we still continue to follow the same silicon-based approach. And we, in this regard, one of the example is development of flexible chips. So what we do is we thin down the wafer from the backside. On the top, you realize electronics first, and then on the backside, you thin it down and you bring it to about 10 micrometer. So when you bring it about 10 micrometer, it becomes very flexible, and you can wrap it around. The chip itself can be wrapped around the surgical tool. Let's say if it has a 5 millimeter diameter, you will be able to then wrap it around, and you can get electronics as well as sensing, touch sensors, all processed locally, and you can get tactile information out of that. But this kind of solution are limited again in terms of area, because fabrication of chip is quite costly affair. And then you have to add the post-process steps, such as making them flexible also. Considering all these factors, one has to, and then looking at the electronic skin or tactile skin, if we have to look at the large area, such solutions become impractical. It's cost effective. It's not cost effective anymore. You have to look at new solutions which drive not only the electronic skin research, but also the electronic research in general. So that leads us to next part, which we are exploring in my group, is printed electronics, high performance printed electronics. Again, looking at inorganic semiconductor devices, semiconductor based structures, because inorganic semiconductors, they have high mobility. High mobility is just one of the factors for high performance. There are other device related or transistor related parameters, such as channel length, which must be as short as possible. There must be ohmic junctions, etc. All of these come together and make lead to high performance. So in this regard, what we are exploring is exploring approaches such as transfer printing, the approach which has been pioneered by John Rogers, as well as approaches such as contact printing. In case of the transfer printing that you see on the top left, what we do is we realize micro nanostructures on the silicon wafer, and they are lifted with PDMS stamp, and then this PDMS, one more transfer takes place, and you are able to transfer micro nanowires on flexible substrates, as you see one example here. Now, once these are transferred, then you can imagine them forming as an electronic layer, which can be further processed to obtain either transistors or diodes or touch sensors or any solid state device you can make from them. And this kind of approach has been used in various applications such as skin tattoo. There are various similar examples available in literature. Second technique is direct printing of nanowires. You grow nanowires, as you see, in a vertical way. There is no need for PDMS, etc. here. And you can just slide them at a particular speed and particular optimum pressure. And you can transfer these wires on any substrate. Any substrate means a flexible substrate or a planar substrate. Once you do it, this becomes the electronic layer, which can then further be processed to obtain transistors or sensor. Now, this is an interesting approach because for electronic skin, you are looking for distributed electronics. And if you are able to print electronic layers on a large area, you can also then use that large area to develop electronics on top of this. So this could, in a sense, if you consider, this could form the backplane. As you see, if you have displays, you have the display and then backplane, which has electronics. So these all can be on the backplane, covered with pressure sensitive rubber or any capacitive or a piezoelectric material, or a transducer material, which can possibly be replaced. These approaches are also interesting because we are no more restricted to, when it comes to realizing electronics, we are no more restricted to wafer size. Example in this animation is about the transfer printing. So essentially you can print from one location, pick from one location and transfer to other location as a desired location where you want electronic or transistors to be fabricated as per your circuit layout. And it can then cover large area. This is one example of this implementation where we see, you can see here the same image where you have nano ribbons and they were transferred on flexible substrate. And this is an example of several, a large array of these devices. We noted that revised response is quite good. In terms of mobility, we got PMOS type device as well as NMOS type device. PMOS gives us about 200 mobility, whereas NMOS gives us 650 mobility. Those familiar with electronics would understand how mobility actually counts to the speed or the speed of the transistor in terms of transistor switching frequency. This is important factor. And single crystal silicon based devices also have more or less similar mobilities when we look at the standard literature. Going forward, this can be further extended. In fact, we have done, but today I have not included that result here, but the scheme only. You can use this approach to obtain roll-to-roll. You can make a roll-to-roll transfer of nanowires and can add fully printed steps to make devices as shown here. So as an example, you define sticky, non-sticky areas, and then you have sort of drum with nanowires, or it could be planar also. You transfer these nanowires, make electronic layers at a location where you need to be. And then you process it further. As an example, you can have high-K dielectric. There are ALDs available compatible with roll-to-roll approach. You can get some more layers deposited in this way. Thin film you can deposit, and you can make some circuits such as one example shown here, which is one transistor and one memristor connected in series. Now, this kind of circuit, if you want, this can also lead to interesting approach solutions for electronic skin, whereby you can have neuromorphic layer, or let's say neural-like computing layer sitting under the transducer. And this is what I'll show you what we are trying to aiming to achieve in my group. Here are some examples of printed nanowires, different type of nanowires, just to show the versatility of the approach. And all equipment that has been used in this case has been developed here in my group. And this is the scheme that shows how it can be used. You have on the back plane, these are the printed nanowires as you see here. And you can then deposit metal lines to make drain, to define source and drain. And on the source, you can have the pressure sensitive rubber, either it can be capacitive sensor or resistive sensor, or it could be even your memristor if you go with the previous image that I showed. In this case, you have the top layer can be covered with the transducer layer as either here, or it can be on top. And then you can see a scheme building something like this one. One cell is shown here. This is transistor, either leading to a capacitive piezoelectric material sitting on top. When you press it, it leads to change in the gate capacitance, or you have the resistor here. When you press it, it leads to change in the resistance. Either way, whatever is the change, it's eventually from electronics point of view is the drain current which is changing. And because it is a transistor and further transistors can be fabricated with the same approach, it makes it easy to integrate the whole complex electronics circuitry. So that's what we are doing in terms of developing electronic skin. There are several other examples which are taking us to computational electronic skin. In the interest of time, I'll skip that part and I'll move to the next part, which is integrated sensing, actuation, and computing, etc. Looking at one example of computing, which we published a couple of years ago, where we again use the same approach that I was mentioning. So, but in that approach, I was just mentioning about how you get the electronic layer. Now, on that electronic layer, if you make multiple gates, and these gate widths you can define it can be hardware, because it's a hardware implemented, it's hardwired. So you can define these gate width in advance and then realize gate. It can work like a synaptic, synapse as you see here. So you got multiple gates. These inputs can be either coming from electronics prior to this device, or it could be directly coming from touch sensors. And depending on how many touch sensors are active, and depending on what kind of stimuli is, they will modulate the channel current. And this then becomes equivalent to the neural network implementation of neural network, where you are able to use weights as the gate oxide, and summation takes place, naturally summation takes place here. And what you get at the drain is the output, some output of all the inputs to the device. Now that was interesting. We also tested this approach using in simulation, where you have 6x6 capacitive sensor array. And this was implemented, neural network was implemented, where you see here that you are able to get, with single contact, you are able to get the contact point, contact force, as well as direction of contact. Now, if you are able to scale down the information in this way, and hardware can be implemented in hardware, the advantage of this is that this type of local computation leads to lesser amount of data, and you are able to effectively use the limited communication bandwidth that you have in a robot or in a machine. It's in the surgical instruments. You are able to send large number of data with or let's say optimally use the limited bandwidth. So this is the advantage here. Another example I mentioned about earlier is in terms of making maintenance, etc. One problem with electronic skin, as we see today, is that we wrap around the surface, and wear and tear is a problem. To address that kind of concern, we have used this new technique where we do multi-material 3D printing, where we are able to print in such a way that structure itself becomes sensor. As an example, the fingertip of robot can be just a sensor. And how does it happen is you start by printing the plastic, then you print the metal, and then you leave, either you can fill it with PDMS or a dielectric, or leave it empty, as air can be there. And you again bring other part which has a conductive and plastic, and you can 3D print the whole structure. And when you 3D print the whole structure, either you can also print the interconnects as a metal interconnects, and use the off-the-shelf components, integrate off-the-shelf components at different layer, different planes. And you can develop the whole hand in this way, or it can be used to develop a surgical instrument in this way. So this is what we have used. Some videos are shown here. Recently, we reported this work where we are arguing that the structure itself can be a sensor. And this, because everything is embedded, and it's in some sense, it is also closer to our body. Everything is embedded here, like sensors, the receptors are embedded inside the skin, and skin is acting as a protective layer. In this case, structure acts as a protective layer, and structure is also sensing. So this part of thing can be taken forward, and some of the printed electronics that I mentioned earlier can also be used in combination with this. Other example here is related to integrating sensor and actuator together. When we talk about electronic skin research, most of the focus, most of the time you will see it's all about sensing. Whereas when we talk about sensing and sensors, receptors in human body, they are embedded in muscles also. So there is a close kind of relation between sensing and actuation. Building on that kind of thing, what we have done, we developed these soft Sensex devices, which is essentially integrated sensor and actuator. What it does is, as you can see from these images, you can press it, quite soft, and it can bend it. And the coil is, it's a electromagnetic coil fabricated using a Bosch process. And total overall structure is about 1 millimeter thick. And what it does is the sensitive layer is a graphite paste and silpoxy on top. When you press it, it becomes a piezoresistive sensor. We have also tested similar approach for capacitive sensor. Underneath is the electromagnetic coil. So when electromagnetic coil is excited, it is able to expand the sensor or squeeze the sensor. This is in some sense, you can see the sensor and actuator action together, as happens in human body also. We have tested these sensors over large, as you can see here, 4 sensors in terms of variability for the same force, as well as very well characterizing in a nice way. And we plan to extend this work further. as an application of this type of work, you can see how sensor actuator is working, and it is able to, if you put a permanent magnet here, it's able to push the permanent magnet up and down, and that way we are able to create the haptic feeling as well. So that kind of sensor on top with actuator underneath, you can see a kind of thickness of movements, and these are shown here. This laser movement shows the thickness mode movements. We are able to generate movements up to 200 micrometer in this way. And as an application, we also connected it to, kind of between deaf and blind communication. We approach this, and what happens in case of deaf and blind communication, they rely on touching fingers and coding. This is the combination of fingers is some sort of code. So, but in this case, if they are, a deaf blind person, if they are, in separate room or they are remotely located, it's anyway difficult. Touch is an important part for them. In such cases, one can think about such solutions. In fact, we developed this kind of smart glove where we have integrated these Sensex type devices, and it will get the sensation as well as through vibration, vibrotactile feedback. It is able to connect to the other end, and we also have an app which allows it to happen too. So you touch sensors, data goes to mobile phone, and then other person's mobile phone will be able to pick that and generates the vibrotactile feedback with which they are able to see a combination either A or B or like that. They are able to feel that. So that way you can see some medical application there with this. Last part of my talk is I can see them. There are 2 minutes left, I think. So last part I quickly want to highlight is related to the area that has not been discussed much in the field of electronic skin, and that is distributed energy or energy autonomy. Now, if you look at our body, and these are the various levels where you can see how our fats and carbohydrates and proteins, they are the generation of energy takes place. Then we have fatty acids, etc., which are kind of storage elements in the body, and these are all over. Why then, if we talk most of the time, we talk about electronic skin as bio-inspired, etc., etc., but that bio-inspiration is restricted most of the time to the sensors. So whereas you look at the energy side, this is all distributed. If sensors are to be distributed, local computing is to be takes place, why not local distributing local energy also? And in that regard, we looked into, recently we published this review article, which is now available. So we looked into various energy generating solutions and energy storage solutions and all over distributing them. And then using them as for sensors and actuators, potentially leading to new design of robots or new design of medical devices whereby energy devices could be used. In fact, energy devices could be used as sensors themselves. As an example, one of the work recently we demonstrated where supercapacitor itself can be used as a temperature sensor or a strain sensor. So why not use an energy device in a multiple way? It generates energy as well as does the touch. And one example, other example that I mentioned about supercapacitor, that's energy storage device. But another example here, which we have reported recently, this is paper appeared earlier in January this year, in January, Transactions on Robotics, is where we used the solar skin, the solar cells, miniaturized solar cells. They were integrated on soft elastomeric substrate. And solar cell is used as a touch sensor in this case. How that happens is solar cell is essentially generating energy when it is exposed to light. When light reaches, it will generate energy. If you block the light, it will not generate energy. If you block the light to a certain extent, it will have lesser light reaching them. And these simple facts can be used. So when you are covering a solar cell, there won't be any energy generated. That means that an indication of touch. If you are slightly away, there will be a shadow because of which light intensity goes down, and that's an indication of proximity. So in this way, you can convert skin as an opportunity, not just a challenge. Large area or distribution is not just a challenge, but it's a huge opportunity for us to generate energy while not adding any new sensor. Solar cell itself is a sensor. So that would be an interesting new direction that we have got. So in terms of energy, what we got was energy surplus 380 milliwatt from the palm area itself. If you consider it, to be full body, which is about 1.5 meters square, you can generate more than 100 watt. That would be good source of energy for moving or operating some of the motors. Some examples, these are last videos, and then I'll jump to the conclusion. So that is one example where you can see the feedback from solar skin used for grasping, and these are the output from the contacted points. And then you have other example is here, which is used for solar skin, is used in the proximity mode for safe interaction. You can see as robot detects the closeness, it's able to move back. So these are some examples in terms of energy skin. This brings me to the end of my talk, and I would like to conclude by saying that touch sensing or electronic skin is very important for safe interaction in robotics, as well as in the case of medical applications where you want to get haptic feedback. Electronic skin with various types of sensors underpins advances in several applications areas such as bionics, healthcare, Internet of Things, wearables, and also smart cities. And printed electronics, which I highlighted as an example of manufacturing route to obtain all distributed or large area electronics, is a promising in terms of cost effectiveness, and it also has a huge implication on electronics, advances in electronics in general. Flexible electronics is one thing which becomes necessary for electronic skin, because you have to put the skin on the curvy surfaces. And in that regard, while it solves the problem for electronic skin, but it also itself is a disruptive area, which is adding new dimensions to the electronics industry, and with enormous impact in consumer electronics, aviation, space electronics, robotics, life sciences, lighting, military applications, telecommunication, and sustainability, which is another topic becoming quite important, perhaps some other time. So with this, I would like to acknowledge the support that I'm getting from my funders, EPSRC, European Commission, Scottish Funding Council, Royal Society, and Royal Academy of Engineering, and my group members who have contributed to the work that I presented. And here are my contact details. Thank you very much.
Thank you, Ravinder, for an amazing talk. A lot of many different technologies presented in a very short time. Fascinating work. We are over time, but maybe we can answer quickly one question that we received in our Q&A. So Karthik Chandrasekaran is asking, Professor, could you please comment on the durability and fatigue life of these flexible electronics?
It's an important question. Durability and fatigue is because at the end, they are all mechanical structure. You have to look that way. So when we look at, we normally try to, bend these sensors for a large number of cycles to understand the durability. It all depends on the material that you are using. Some materials would fail after 50 cycles, whereas others would continue to work for a large number of cycles. Ultra thin chip, as an example, there's a limit up to which you can have repeated bending, and if you cross that, then it gives away, it'll crack. And fatigue is also, in some sense, I would say, taking an example of ultra thin chip, if you keep it bending for a long time, you can see some signals, the transistor response changing because of the piezoresistive behavior. So fatigue it gets reflected in that way. Now, this can be a problem if you are not using any, if you see over a long period of time, but this was also an opportunity. As an example, the change that you see because of bending, that change itself can be used as in a way can be used as sensor. And we recently demonstrated this in case of ultra thin chip. We developed ion sensitive field effect transistor, which is popular sensor used in biosensing application, but ISFETs are prone to drift. So we demonstrated that by controlled bending, you can compensate the drift, and you don't need electronics, dedicated electronics to do that. So one could argue about the arrangement, that the bending itself would be a cumbersome arrangement, etc. But point I'm trying to make here is that this is an opportunity as well.
Fantastic. Thank you very much. And it was a pleasure to have you.
Thank you.
We have now to move on to our next speaker. We have Benjamin T. He's an assistant professor in material science and engineering at the National University of Singapore, and he leads the Sensors AI group over there. He's going to be talking to us about materials and systems for scalable and sustainable intelligent systems. Your floor is all yours, Benjamin. Thank you for being with us.
Okay, thank you very much for organizing this exciting workshop on soft robotics, especially for medical applications. Hope everybody can hear me well. Is it, and the screen is showing properly? Okay, great. Yeah, because there was this really funny story where this lecturer talked for 1 hour, and at the end of it, it was found out that he had been muted the entire time. So anyway, it's just a funny story. I hope everybody's staying well in these really unprecedented times, and I'm really happy to again meet virtually many of the panelists who I've met at conferences just almost feels like a long time, but 2 years ago. Hope everyone's doing well. I'm Benjamin T from National University of Singapore. So I'm also very interested in healthcare, and in fact, I was quick background is I actually did the Stanford Biodesign program because I wanted to apply technologies that I developed from the lab when I was at Stanford and translate them to a real use case, especially for medical and clinical use. And so I joined the biodesign program. And through this program, I really understood how difficult, or rather how challenging it is to develop technologies from the lab and bring it all the way to actual use by doctors or by patients. And this really, due to the regulatory environment, and there's just a lot of more considerations when you're translating. So, if you have any questions that you're interested in that aspect, let me know. I've started a couple of companies now who have gone on to raise, I wouldn't say a large amount, but some money, and we managed to get clearance for some of these products. I've gone through FDA clearance, CE mark as well. So, these are all a lot of effort actually from the lab to bring it to regulatory clearance, and a lot of resources are needed as well. If you're interested, you can also add me on LinkedIn. And I run the Sensors.ai labs. We work on a few different areas, broadly classified into 4 areas: mechanical sensing, which I think I follow the footsteps of Professor Ravinder Dahiya. He was one of the pioneers actually in this field, and we learned a lot from his work with ICAP. Also very interested in self-healing materials because actually my home department is material science, and I think that self-healing materials can present some possible solutions to address sustainability challenges moving ahead as we start to consume more and more electronic devices. I'm also very interested in neuro-inspired work where we look at how the human nervous system operates and how we can learn from its efficiency and its elegance in terms of data processing and cognition, right? There's a lot about AI, and I think learning from human brain, which is only 100 watts or less of power, compared to gigawatts for supercomputer, could be interesting way forward. Now, of course, stretchable electronics, and I think that that's really is sort of the important point in this when you're trying to marry electronics with soft tissues found in biological systems such as the human body. And of course, you can always have my emails and add me on social channels. So I'm going to talk a bit about touch. As I've mentioned, I think touch is a very crucial part of intelligence. In particular, the human brain fuses many streams of information. Vision and touch happens to be almost critical in all aspects of daily activities that you are performing, right? In fact, if you look at clinicians, right from the ancient times, they've been using the skin and touch as a medium to understand the body, right? If you feel something's a little different, whether it's maybe stiffer, harder, a lump, you can kind of try to see whether there's a problem, right? And that's sort of how physicians have used touch. In fact, this is a routine screening procedure by clinicians, palpation, to determine if you have any possible need for further interventions or diagnosis needed, right? So the skin is clearly very important, and there's a lot of exciting technologies from Prof. Ravinder's lab and many others, right, looking at solving the challenge of bringing touch to machines. And in a medical robotics, I think medical robots have to perform very complex tasks. If you look at Da Vinci as a platform, Da Vinci surgical robot as a platform, which is one of the earliest robotic systems that was brought through regulatory clearance to market. Of course, they're now a very, very big company, right? Hundreds of billions of dollars in market value. They require a human, right, in the loop to actually operate the machines that actually perform surgery in keyhole surgeries in humans. And I think there's some exciting work in material science and also soft robotics fields where we are looking at developing strategies to allow some of these procedures maybe to be performed by robots. Could be autonomous, could be remote controlled, right? I think soft robotics, soft materials can play an increasingly exciting and important role once you want to interface with the human body. And one more point I want to make is that the miniaturization is very important, and I think Professor here has mentioned that silicon technologies is one of the workhorse of all electronics, and I think that's absolutely correct. And I think that the ability to miniaturize silicon technology, silicon microprocessors, can also play a role when you try to make soft materials intelligent, right? So you can increase the functions of soft materials to perform computation, very basic computations, and they can be all shrinked in a very tiny package, right? In this case, smaller than a fingernail even. So other areas, I mean, many people have really looked at exploring. My group, I started about 2017, end of 2017, and we looked at self-healing materials as well as mimicking nervous systems, which I'll talk a little bit about today. I'll talk about self-healing a bit more, but mimicking the human nervous system is also a big area to make materials more intelligent. So I think in terms of medical robotics, perhaps, I'm not sure, but I think the holy grail could be that you can swallow the doctor, right? As Richard Feynman has pointed out, back in 1959, where he gave a lecture and said, if you can swallow the doctor surgery in performing surgery in the body, it'll be a very interesting proposition. And so I think that's kind of where we're already starting to head towards, right? We're having pills that you can swallow. They can take pictures of your guts and maybe look at whether there are anomalies. And so these are already starting to happen, and there's a lot of other researchers developing different technologies that you can sort of put into the body non-invasively or sometimes minimally invasively, right, to actually contact the body and perform interventions. So one of the biggest challenge, I think, working with the human body is that we actually have a very left end of the spectrum, right? Whereas all the materials that we are used to perform intelligent functions are right at the stiff end of the spectrum, right? If you look at Young's modulus, which is a way to measure how stiff something is, silicon technology is the workhorse again, but the gigapascals, hundreds of gigapascals. Metals, they're all hundreds of gigapascals, but they work very well, right? But if you look at skin and other soft tissues like the human brain, for example, if you perform brain surgery, all these things are extremely soft. They are almost like jelly that you eat, and they're only hundreds of pascals to megapascals. So there's a lot of challenges when we interface rigid materials that we know can perform good electronic functions with human tissues, just because of this a big disconnect, a big gap in the modulus, right? And I think this can be exemplified by an interesting photo. Actually, this person has a skin that can stretch more than twice the average person. Definitely don't try this at home, but it brings home the point that trying to bring electronics closer to skin requires them to have a certain degree of flexibility, stretchability, and softness. And I think one of the biggest challenge with integrating many of these technologies that are soft and stretchable is the ability to conduct electricity across devices. And so my group, we started thinking about this problem, and there many other researchers have done really nice work looking at nanomaterials, metal nanoparticles. These are all ways you can make them stretchable when you reduce the size of these elements. But we wanted to work with bulk materials, so we started with bulk materials because they have very intrinsically high conductivity, right? But usually they don't have high strain. So we came out with sort of an e-helix, almost like mimicking the DNA, right? DNA is a helix, and kind of thought about what if we could make wires in a helical manner and embed them within an elastic substrate. Will we be able to stretch it? It turns out that's kind of obvious, but what's not obvious is the mechanics and interfacial properties of embedding the metal into a soft elastic substrate. So here you can see this video shows an LED connected by the metal helical wires, and the LED brightness is not changing as you strain the conductor. And so this basically means that the conductivity is not changing with mechanical strain, and these are about 100 to 200 microns metal wires. And so you can strain them to 150%, and the conductivity remains very high, right? In fact, it's pretty much invariant. But the mechanics of it is quite interesting, and we actually started looking at this as well, and we found that actually you need an appropriate volume of the elastomer to the metal wires in order to have this ability to restore itself. If you have a low volume of elastic material to the metal, you actually do not recover what we call the residual stress. So when you stretch the material, what happens is some of the energy it gets dissipated, and when the elastic material does not have enough energy to bring the metals back, they have a residual strain. And so we found that having a ratio of roughly 5 or so to the diameter of the metal wires, that gives you a pretty good residual strain of less than 5%, which is mostly negligible. And well, this paper is still being under review, but hopefully you'll come out soon where you can read up more on the details of the mechanics of such systems, such hybrid hard metal, stiff metal, and soft elastomer systems. So another thing that it's important when it comes to the skin is that it can sense mechanical forces very well. In fact, every single cell that you have that we know actually has the ability to sense mechanical forces, right? And so having ability to sense the environment through contact is something that nature has found is very important. It's the first sense organ, in fact, skin to develop. And so looking at mechanics of materials, we can design them to be more sensitive than they are by structuring them. Using soft materials gives us an advantage because they can be a lot easier to shape or mold, through techniques such as soft lithography or injection molding. And so we can mold shapes such as pyramids, and we can concentrate stress at very specific areas so that we can allow the strain to be enhanced, right? Just because of the properties of the material by its modulus. Since modulus is stress divided by strain, having high stress gives you greater strain, right? For that particular structure. So in our lab, we are studying such structures a bit more closely at a single structural microstructure level, and so we are getting equations that we can model such performance or such change in mechanics as you compress, right? And here we show capacitance versus strain. So capacitance is a way to measure the properties, mechanical properties of such structures, and it gives you an indication of how much force you're applying. And so, having such models that well matched with experiments can allow us to build such engines that allow designers to design sensors that they need of any sensitivity or working range that they want. And so using such systems, we can design sensors that can respond to soft and stiff tissues, right? Here's an example of a AR system where we have developed materials, sensors that can respond over a broad range by design. And so what you see in the video is basically different kinds of tumor types, soft and hard tumor. And we sort of developed a sensor mat that can train surgeons when they're doing cutting actions through some form of AR system. So what you're seeing is through the screen of a smartphone, and you can see that as the surgeon depress on the material, underneath the material is a pressure sensor. You can actually see how much deformation is being achieved, and also whether you're holding the scalpel steadily or not, right? So there's some use there. Beyond just going to the body, you can actually train the surgeons better, a lot easier than using cadavers before they move on to more expensive training procedures like using cadavers. So another challenge with soft materials is that they have this property we call viscoelasticity. They're nice because they're sensitive, but at the same time, they can have time-dependent strain performance. And so basically this is something like a memory foam, right? If you have a memory foam pillow, you depress it and you remove the weight, what happens is you see this slow change to going back into its original shape. It's called viscoelasticity. And the softer the material, the greater the viscoelasticity, right? So we wonder if we could tackle this by making soft materials behave like metals. And it turns out that we can do that if we take a hybrid approach, again, combining stiff metals on soft polymers. And so here's an example of one hybrid system where you have metal films on top of the microstructures we know can compress and sensitively, right? And we found that actually we can crack these films quite easily. You crack these films, you can modulate the resistance. But the problem with random cracks when you press on such films is that the performance is not repeatable. And so because you can see that these cracks are formed in a random fashion, and this makes your sensor not so reliable, right? And what we found is that if we take a soft layer and we apply the same compression, control compression, we actually get very nice angular cracks. And these nice structures actually give it the ability to sense mechanical forces more reliably with less hysteresis, right? So here you can see if you have a random crack, you almost have an on-off kind of switch. But when you have annular cracks, you can see some nice pressure induced resistance change across the electrical properties of the film, right? So you can see that the hysteresis, which is shown by the window between the forward and backward sweep, is actually very low, right? Less than 5% compared to typical soft polymer films that are conductive on the same structure. And compared to different sensors, we do see that we have a good sensitivity versus hysteresis, right? And in this case, we're plotting 1 divided by hysteresis, so the larger the number, the less the hysteresis. So using techniques we learn from neuroscience and mimicking biology, right? We also develop systems that can transmit all these sensor data very quickly. I don't have much time to go through this for this workshop. But you can feel free to read out a bit more, but we can have an asynchronous method of transmitting the data from the sensor I described earlier, right? And we can have very high speed relative to human skin. So we can technically detect mechanical changes much faster than a human can. We are operating at very high speeds across large numbers. I think that's sort of a unique proposition we have for this system we call ACES. And so we can put large arrays of our sensors, the metal film crack sensors, and we can actually detect textures, for example, roughness and so on. And we can actually show that we have better classification accuracy for the different type of textures versus a sensor that has more hysteresis, right? And the error bar for high hysteretic sensors, highly hysteretic sensors are actually much higher, whereas we have a lower standard deviation and also a better accuracy. The x-axis is contact time, so how much time you have contact with the surface. And we do see it saturates, using our sensor, it saturates very quickly at about 90% with fairly low standard deviations. Okay, so I have about, I think, 10 minutes left. So I'll spend the last part of my lecture talk actually talking about self-healing, right? And I think skin or organic systems have the ability to self-repair. And this results in hopefully less waste and more sustainable electronics if we can mimic aspects of biological system such as skin. And one example is if you break your phone, if you drop it, it doesn't repair itself, right? Wouldn't it be wonderful if it can repair itself? I think this may lead to less electronic waste being generated. And so my group, we started looking at self-healing materials that might behave as sensors, as well as having the ability to perform certain electronic functions. Right? So we made use of molecular interactions of materials, in this case ion dipole interactions, by putting ionic gels into ionic liquid into a polymer to make an ionogel material, right? And so these ionic dipole interactions are quite strong. So when you damage the material, they can actually self-repair. Here's a video showing how this works. So we can have this material which is very transparent. So it has optoelectronic uses as well. So you can see we cut the material, placed it separately, and put it within water, completely surrounded by water. And after some time, when you remove it out of the aqueous environment, what happens is we do see that the material at the interface starts to heal again, and regains its mechanical functionality and properties. So we can have such materials because they're conductive and transparent. There are uses such as human-machine interfaces, playing games and so on. But one can imagine having such materials for controlling surgical robots, or actually putting such materials within the body, because the material that we use is actually is what sutures are made of. But we will have to replace the ions that we use to make it more biocompatible. So another interesting way we can use such materials is to make them generate light. And when we started the work looking at whether we can make self-healing devices that generate light, there wasn't really any self-healing light sources when we started the work. And so one strategy to make stretchable light sources that can potentially interface with soft tissues is this device called light emitting capacitor, right? A capacitor is essentially a sandwich structure with a dielectric in between. Right? And so there's nice work by Shepard back in 2016 showing stretchable electroluminescent displays. And basically, one challenge with such materials is the light source is very dependent on the frequency and voltage. In fact, many of these devices do need quite high voltage to operate, usually thousands of volts. And so we said, well, maybe we can try to investigate, right, whether we are able to make devices that have low electric field capability and yet high brightness. Ideally close to mobile displays, which are about 200 candelas per meter square. In fact, if you look at many of the reports, they're generally limited by the material. They have low dielectric constant. So we set out to develop a high dielectric constant material by using PVDF type materials and incorporating some additives, right? They actually made it self-healing. At the same time, makes it more stretchable and doesn't affect its ability to have high dielectric constant over high frequencies. So this is kind of a simple experiment where we cut two materials where these particles generate light. We embed them into such a structure and can see that they can heal at the interface when you place them together, right? If you cut the materials and you put them in the interface, you try to stretch it, it doesn't break apart. So that was quite surprising that it could self-heal. And in this case, this material isn't a conductor, it's actually an insulator behaving as a very good dielectric. And so this allows us to get very high luminance, over 1,000 luminance for fairly low electric field. So electric field is the voltage you apply divided by the distance between the electrodes. And so here's a video showing that our material compared to traditional light emitting devices, soft light emitting devices, they are actually very bright. And these are all done in bright daylight, ambient luminance lighting. So you can see that they're very much brighter than traditional low dielectric constant materials, and almost comparable to a cell phone. Although this is not, this is mostly, this is not so scientific, right? But we actually used a proper setup to measure this. This is just by human eye. You can see. By human eye is a bit hard to quantify, right? But that was just a quick experiment. So the reason it works is it can have very high dielectric constant over a broad range of frequencies compared to silicone materials that are typically used in soft electronics. So such material allow you to have very low operation voltage. So if you take a silicone material with high operating voltage and you puncture them with a needle, what happens is the light doesn't really light up. The device doesn't light up, and also when you try to turn it on at such high voltage, because there was already a mechanical defect, it actually causes electric breakdown and burns up the device. But if you use the material with high dielectric constant, right, material, we can actually have we can have fairly bright, much lower electric fields, right? Although the voltage is high, electric field is low, but when you puncture it and you turn it on, there is still some light compared to the earlier silicone-based materials. But what's interesting is you can regain its luminance, almost 100% when the needle is removed. So we can think of robots, soft robots. I'll be happy to discuss how this can be used in medical robotics. What we have is we have a light source, we have a light sensor. We can detect objects, and we can perform actuation by using soft materials like a soft gripper, right? So we can also do wireless powering. As mentioned, Professor Ravinda mentioned, powering devices can be challenging, especially if they are inside the body, which actually presents very difficult challenges because electromagnetic waves doesn't like to go into the body, which is why you don't get fried by the Wi-Fi and all this Bluetooth, right? So anyway, we are able to show that our device, because of our material, we can power this, what we call Helios devices, at fairly low voltage, so they actually turn on compared to the control, which doesn't turn on at the same operating voltage. So, so now finally we are starting to piece together different of the systems that I've showed into a video that shows a robot actuated by by magnetic fields. Fields, for example, an MRI machine can generate. And you can actually see that these such soft materials can move around. In this case, we have not. This case, we didn't wirelessly power the light source, but we have shown that we can do it, just not in this video. And you can see that you can actually make soft robots move without any mechanical contact. It's purely just by driving them with electromagnetic fields. And lastly, I'd like to end by saying that actually, even in science fiction, today, we're seeing a lot of technologies envisioned by science fiction writers like Isaac Asimov, who talks about medical robots, right? And in the Fantastic Voyage book. And I think that many of the technologies we are developing will start to converge to make, hopefully, in the future, surgeries pain-free and also as simple as swallowing a pill. So I'd like to thank many of my collaborators and the funding agencies, and of course, the group that keeps me young. All right, thank you so much.
Thank you, Benjamin. Very, very exciting work. I don't see any questions in the chat, but maybe I can ask one. Basically, you also hinted to this question, is what would be the biomedical applications for these electroluminescent devices, and also the self-healing characteristics of this?
Well, I think it's still early stage. I mean, it's a good question, right? It's still quite early stage. So for me, my interest in developing self-healing materials is because I want to hopefully reduce electronic waste. I mean, we're definitely generating a lot of e-waste. In the future, it could, and then probably non-invasively, could be sort of in certain bandages and things like that. But it's still, I'm not. I would love to talk to doctors who have interest in such materials, but I don't have any use case in particular for medical robotics yet. Yeah. And
one last question, and then we can break. Go for the break, for 5-minute break, is with regards to those pyramids you demonstrated with the deposited metal films and the cracks. Are they reusable, or is it a one-off use? Once they crack, you do the sensing, but then... Okay,
yeah. That's a great question. Actually, we were also curious, right? Actually, what happens is when you form the annular cracks, over many cycles, it does change, but we found that the annular cracks dominate the rest of the mechanical behavior. So they actually do last over tens of thousands of cycles without significant change in the sensitivity, right? But of course, I think over time, it will definitely not work after about a million cycles, but I think it depends on your use case. If you have tens of thousands, hundreds of thousands of cycles, should be all right.
Thank you very much for joining us. And now we need to
Thanks a lot.
break for 5 minutes.
Fantastic talk. Thanks a lot. Thank you.
Yes, so we'll do a 5-minute break, and we'll be back at 17 past.
Thanks. Bye-bye.
Hello, welcome back from this short break. Our next speaker is Professor Carmel Majidi. Welcome. It's a pleasure to have you with us.
Thank you.
Carmel Majidi is a professor of mechanical engineering at Carnegie Mellon University, and he leads the soft machines lab over there. And he works on the development of novel material architectures that allow machines and electronics to be soft, elastically and formably and biomechanically compatible. A lot of his work is around fluid film elastomers that can function as artificial skin, like the nervous system, tissue, and muscle for soft robotics and wearables. And he will be talking to us today about soft robots that feel and multimodal sensing schemes for soft robot grasping. Your floor is yours.
Thank you, Panos and Kaspar. It's a real pleasure to present, and also honor to present after Ravinder and Benjamin. They both gave very excellent talks, and I'll do my best to follow up. And I'll be touching on addressing some of the same themes. So I think it's this is a really nice kind of series of presentations, and I'm also really looking forward to Sheila Russo, who will be presenting after me. The work that I'm going to cover will touch on what you've heard already from Ravinder and Benjamin regarding soft electronic skins and sensors. I do want to emphasize some of the work we've been doing with soft robot grasping and the integration of these skins into those grasping systems. Now, I do want to start off by acknowledging the people who've actually done the work. I'm really more or less the spokesperson. Everything I'm going to present here has been done by my amazing team at CMU, the Soft Machines Lab. And in particular, I want to acknowledge Tess Hellebreakers and Eric Mervichka, both former PhDs in my lab from the Robotics Institute, who've done the bulk of the work that I'm going to show. And I also want to acknowledge our faculty collaborators, Oliver Cromer within the CMU Robotics program, and also Mahmoud Tavakoli at the University of Coimbra. So I think Ravinder did a really nice job of kind of motivating why we're interested in soft materials and soft robotics. And so I won't really spend too much time on this slide. Just from my perspective, really the goal here is to engineer machines and electronics for robotic systems using materials that are orders of magnitude softer than what we've traditionally used in engineering. So instead of the hard metals and plastics and ceramics, we're instead working with soft gels, elastomers, fluids that have mechanical properties in terms of their deformability or their stiffness, much more similar to soft biological tissue. And so this is kind of what I mean by soft matter engineering, basically engineering machines using this class of condensed soft matter materials. Now, why is this important? Well, again, Ravinder and Benjamin did a fantastic job of presenting a lot of the breakthrough work and a lot of their own pioneering contributions to this area of flexible and stretchable electronics. And needless to say, there's a variety of different architectures and approaches to creating these types of electronic systems. And so, pretty much all of these have kind of come up. So these ultra thin films and these so-called deterministic architectures where we have kind of wavy or serpentine type interconnects. Benjamin showed some very nice work with this kind of coil or spring-like stretchable interconnects. There's been tremendous work in nanomaterials by the previous speakers as well as others. So the bulk of my presentation is going to focus on soft microfluidic electronics, in particular using liquid metal alloys like gallium, indium, eutectic. And then Benjamin ended his presentation presenting some really beautiful work on various types of conductive and dielectric hydrogels. And so I'll just kind of briefly touch on that at the end of this presentation. What I do want to emphasize is, and as you've heard, that there's other applications of these soft electronic materials. Haptics, of course, being one. Ravinder shows some really nice work on that. I'm not really going to spend too much time covering work from my lab. I really want to focus more on these soft robot grippers, but that's certainly one area of kind of current interest. And another area that both Ravinder and Benjamin had brought up up was energy harvesting and self-powered electronics and sensors, another area that I've been very much interested in. We've had a couple of recent publications, but also I'm not going to present on that work just in the interest of time. So, and then lastly, soft robotics is another area where there's been a lot of kind of focus in applications of soft matter engineering. So, Caspar, is kind of a pioneer himself in this field and applying it to kind of medical to applications in medicine. And generally, I would say that the community in the UK has done, been a real pillar in this work. So I'm not going to spend also too much time on soft robotics, but this is kind of in the background of a lot of the work that we're doing with these kind of soft and highly stretchable circuits and sensors. So a common challenge in all these fields is materials integration. In a lot of cases, to have practical systems level type applications, it's not enough just to have these soft sensors and circuits and actuators. At some point, we have to interface with the rigid microelectronic components, whether it's a microprocessor, a Bluetooth transceiver, a lithium polymer battery, whatever it is. And so that oftentimes what we found is that a lot of our manufacturing methods have to be kind of versatile enough to enable this kind of robust interfacing between these IC chips and condensed soft matter. Okay, so going back to this kind of overview of the different architectures, I'm just going to go through these topic by topic, and I'm going to cover a lot of these fairly quickly and focus mostly on the liquid metal circuits that we've been working on in my lab. Regarding these ultra thin and deterministic materials, our contributions have been relatively modest within this field. You've already seen some really kind of nice work on this. Really, our kind of focus has been more on using rapid prototyping tools like UV laser micromachining, so that we can create these thin and flexible circuits rapidly on the order of minutes or hours. And so here's just a few examples of fully wireless sticker-like electronics that are created using these rapid prototyping techniques. And so you can see at the bottom, we can incorporate different types of sensing chips. These are all accomplished using just commercial surface-mounted microelectronics. Here's an example of doing a pulse oximetry using one of these commercial photonic chips. We have a Bluetooth transceiver, onboard coin cell battery, so everything here is wireless. Here's another example of just using these stickers to augment a humanoid robot to give it a sense of touch, but also kind of superhuman sensing, in the sense that we also have the photonic chips here for doing proximity sensing using time of flight. We also have a pulse oximeter here, so that this humanoid robot is capable of measuring heart rate and blood oxygenation. So this is the Robonaut 2. It's the humanoid robot developed by NASA in collaboration with GM Automotives, and this is in the International Space Station. Although all the testing that we did here was in the NASA facilities over in Houston, Texas, in the Johnson Space Center. And so, as you can see, these electronic stickers are good enough. There's nothing really too exotic going on. We're just using these kind of commercial chips, putting on a highly flexible or stretchable sticker-like circuit board, and then we can just kind of slap these on to the fingers of the Robonaut, and basically have it do this proximity detection, so it can kind of scan and 3D objects to do kind of object kind of reconstruction, and then it also has this pulse oximetry chip, so when it's in contact, say with your finger or your wrist, it can measure your blood oxygenation or your heart rate. And so this is just kind of showing basically what we can do with kind of these kind of more established type of architectures. And then lastly, here's a video. This is collaboration with Lin Yao's group, who's in the CMU Human Computer Interaction Institute, where they've created these design interfaces, these user interfaces, so that even a non-expert can go and create these circuits, and then use our rapid prototyping tools to create these soft electronic stickers. Really the message here is that with this architecture, you can incorporate virtually any type of photonic, CMOS-based or MEM-based sensing modality into a wireless sticker. Then you can just place on the body. Sorry, I didn't mean to skip that video, but and you can stick it on the body, and you can get, say, motion tracking in the case of stickers that have IMU, inertial measurement units. We can also get, this just shows you how stretchable it is because of the serpentine type geometry. And then we can also do, say, acoustic sensing, say if you want to monitor like food intake. You can do temperature sensing, again, pulse oximetry, and other types of sensing modalities. So that's kind of what we can do with this kind of more established type of material architecture manufacturing method, but there are limitations. Just very quickly, in the case of these serpentine type interconnects, because we're interfacing with a very soft and elastic carrier medium, we do get stress concentrations and we do get delamination. So this limits our stretchability to about 50% strain, which is actually good enough for a lot of wearable applications. But it is limited for certain medical applications and also for more generally applications in soft robotics. And so we've kind of looked at other material architectures. Nanomaterials is also quite well established, but still an area of intense research. There's kind of a lot of still a lot of opportunities here for progress. And so, but traditionally people have used either carbon filler or silver flakes or silver particles to create percolating conductive networks within a soft rubber, and this has been also effective for us in creating soft electronics. Now, an outcome of this work has also been spin-off companies, and so one of my former postdocs, Alex Farlambides, launched a company, Life4 Labs, in collaboration with a few other co-founders. And so that work is kind of focused more on medical applications of these types of wireless stickers. And so I can't really delve too much into the details of that because a lot of that's still very much a work in progress. But Alexei has been able to lead a lot of really exciting studies in terms of utilizing these in the operating room, using it to kind of assist in physiological monitoring, say during surgery or post-surgery. So in silicone, I want to spend a couple of minutes talking about the work from Tess Hellebreakers, because I think this really does kind of fall into the theme of this workshop session, which is how we can use kind of embedded sensing and these kind of sensorized materials to augment the capabilities of soft robotic systems that could eventually be used in medical applications. And so this is a material architecture that Tess developed, and it is somewhat kind of related to other efforts of using magnets for tactile sensing or deformation sensing. Whereas past work kind of focused on kind of larger magnets, but what Tess developed was a method of embedding these microscale magnetic particles. These are neodymium the particles, about tens or 100 micron, and have a suspension of those inside rubber. And basically each one of these little magnetic particles functions like a little sensor. As the rubber, as pressure is applied to the surface or as the rubber is stretched, these particles will move and they'll rotate, and that will induce changes in internal magnetic field. And that magnetic field, change of magnetic field, can be detected by an embedded magnetometer. And so I'll talk a little bit later about our liquid metal electronics, but with this device, we're able to incorporate a 3-axis magnetometer that's wired up using liquid metal traces inside of this rubber. And so because the wiring is liquid metal, the rubber can kind of stretch or the circuitry can kind of stretch into form with the surrounding rubber. And then, like I said, as pressure is applied, depending on the magnitude and direction of the change in magnetic field, we can kind of roughly detect what the location intensity of that pressure is. Now, in principle, it sounds pretty straightforward, but because of the stochastic nature of all these microparticles suspended inside the rubber, it's actually very challenging, if not impossible, to come up with a deterministic mapping between that change in internal magnetic pressure with the location and intensity of contact. So what we have to do is use machine learning algorithms and then various regression and classification schemes to establish those mappings. Now, the advantage of this approach is that we're able to do continuous tactile sensing over over a large area using just a single sensing chip. So with just a single magnetometer, we can basically get, we can detect contact at various locations over the surface. And so this kind of represents, for us at least, an advantage over past techniques where we needed basically a sensing chip or kind of sensing node at every single location where we would want to detect. And so you would imagine that to get high resolution sensing, that would require kind of a lot of wiring and a lot of sensing chips. So this allows us to eliminate all that and achieve continuous sensing over a large area with just a single chip. So like I said, we use machine learning algorithms, and then once when we train our classifier, we can then go basically use this pad to do all sorts of tactile sensing or sense contact with a robot. And so I'll just kind of show this video here of Tess playing this game of Miss Pac-Man, basically using this sensing skin. And again, this is all accomplished just using a single magnetometer chip. And as you can see, once the classifier is trained, the sensor is fairly robust and can operate in real time. Another embodiment of this magnetic sensing skin is to basically used in conjunction with a robot where the magnetometer, instead of being embedded in the sticker or in the skin like it was before, is placed on the fingers of the robot, and the magnetic skin is placed on whatever object it is that you want to manipulate. Now, the advantage of this embodiment is that the magnetometer is not just detecting deformation of the magnetic skin, but it can also detect proximity. So as you get closer to this magnetic skin, right, that magnetic field strength increases. And so basically the gripper can kind of use that magnetic interaction to locate the object, and then it can basically use the, once when it's in contact with that object, it can use the deformation of the magnetic skin to determine the intensity of force or the intensity of pressure. So it knows is basically how hard it's squeezing on that object. So just this single material, but it allows for this kind of, in this case, this multimodal type sensing of both proximity detection for object location and then pressure sensing for modulating the contact. So I think this video hopefully kind of captures the principles here. So this is just kind of fabrication of these. So we just mix in the magnetic particles into the rubber, and then we magnetize it, place it on our object, in this case a key. And the goal now is for the robot to pick up the key and put it into the lock. So it basically uses that magnetic sensing to detect the location. It located it, it picked it up, and now it basically is placing it in, and now it's basically detecting the force and torque that it's applying. Here's another example. Let me just pause real quick. Here's another example where the gripper is, again, using the magnetic skin to locate the object. In this case, it's a pipette. And then it's going to be using basically the pressure sensitive nature of the magnetic skin to modulate the force that applies to this pipette. And so it can do this all kind of autonomously and perform tasks that otherwise would be impossible or very difficult to do with just computer vision and cameras alone. And you can kind of see the camera here off to the side, but that will tell you, that'll help you with maybe locating the object, but it won't help you with determining what the pressures and the forces are. So it goes and contacts the object and is able to modulate the pressure, and so it can get different volumes of liquid to come out of the pipette. So you can see now it knows it's using basically the embedded pressure sensing or the intrinsic pressure sensing now to do this kind of closed loop feedback, where it's now able to dispense kind of larger volumes of fluid. So just to move on here, general issues with these particle-filled elastomers is that in order to improve the electrical or sensing performance of these materials, we have to load them up with higher concentrations of these particles, but because the particles are rigid, that will result in increased stiffness, a lower strain limit, and also can contribute a great deal to kind of mechanical hysteresis, inelasticity, and also electrical hysteresis. And so there's kind of a certain limit also with using these particle-filled elastomers. And so our approach has been to instead look at liquid metal filled composites, where because the metal is liquid phase, we can overcome a lot of those limitations in terms of the influence of those inclusions or the filler particles on the elasticity and mechanical compliance of the surrounding rubber. So I really need to credit Michael Dickey, who has done a lot of the pioneering work on this topic that my group has adopted over the years. But I should also point out that the use of liquid metal in soft electronics and in medicine dates back decades, all the way back to the 1940s and 1950s. And in fact, the pioneer of this, Reginald Whitney, was a professor of physiology at the University of Oxford and used this for a lot of his studies on biomechanics. So this is it kind of just gives you a flavor of how we can interface microchips with these liquid metal traces. We use a HCl vapor to basically remove the oxide skin that forms on the liquid metal, and that assists in allowing the liquid metal to form robust connections with the pins of whatever surface mounted chips that we have. And so here's kind of a demonstration of a 9-axis IMU along with a temperature sensor that has this liquid metal circuitry and these embedded microelectronic chips where we have these direct connections. So, like I said, I mean, a lot of our focus has been on applying these soft skins to soft robot grippers. And so the way that we actuate these grippers is using shape memory alloy. And so this video here that I just ripped off of YouTube shows a very commonly used shape memory alloy. It's called nitinol, or it's a nickel titanium alloy that at room temperature is very compliant and highly deformable and malleable. But then when you heat it up, either with external heat or by passing electrical current through it, it basically recovers its shape. It becomes much stiffer, and it goes back to basically its original geometry, which in this case was this coil. So this is kind of the principle that we're leveraging. And I want to credit folks at University of Bristol in the UK who did a really nice implementation of incorporating these coils of shape memory alloy into this kind of soft robot actuator. And so this is kind of the approach that we've been adopting in a lot of our designs. And so here's this kind of one example of a starfish-inspired untethered soft robot that has an onboard battery here, and it has basically shape memory alloy powered limbs that allow it to kind of move around. This video is in real time, by the way. The ability of this robot to track this ping pong ball is done with the aid of an offboard camera, and so there's basically this closed loop control here. And the work that Tess has done with these soft skins also incorporates these coiled shape memory alloy actuators, and she uses that basically to bend the limbs. And then, as I'll show you in the next couple of slides here, she's taken that liquid metal circuit, populated it with all sorts of different types of sensing chips, and then just wrapped it around the fingers of the soft robot gripper. And because the liquid metal circuitry is soft and deformable and highly stretchable, it can conform to this robot and operate without interfering with the natural motion of the robot gripper. So this is just the sensing skin before it's placed on the robot gripper, and there's IMU, pressure sensors, temperature sensors, time of flight, proximity sensors. So all sorts of different sensing modalities that we've incorporated into this. So we've taken that, we've wrapped it around a soft robot gripper, and this shows you how having all those sensors on board enables a certain degree of kind of autonomous robot interaction with objects. And so first we're using that onboard time of flight sensor to detect this object. And then when the gripper has detected the location of the object, it'll go and attempt to grip. And you'll use its pressure sensors to know that it's successfully made contact with the object. And then there's an IMU there also that's tracking the kind of orientation and the motion of the gripper. And so just to show you how this process is autonomous, here we're going to introduce disturbances. So we're going to let the gripper identify the object, but now we're going to suddenly move the object. So the fact that the object got moved, that disturbance was detected by our time of flight sensor. And so the robot knows to go and reattempt the localization. And again, when it goes to pick, we're again going to disturb the operation by kind of preventing the gripper from lifting up the object. And so this is something that's going to be detected by the onboard pressure sensor, right? So the robot knows that it did not successfully lift up the object, so it should go attempt it again. And so anyways, that, I mean, gives you kind of hopefully a flavor of how these types of onboard sensing skins can be enabling to allow for autonomy of these robotic systems. All right, so just a couple last demonstrations here of this sensing skin. Here's just kind of another application of this. Here, instead of using a commercial barometric MEMS pressure sensor, we're using the liquid metal itself as a pressure sensor. We can do, again, localization and also detection of successful contact and lift of objects. And again, using machine learning schemes. Once when we've kind of adequately trained our classifier, we can use these onboard sensors to successfully track whether the robot has achieved close grip and successfully lifted up the object. And with a trained classifier, in this case, long short-term memory classifier, we're able to get fairly good accuracy with this, at least for a fairly wide range of different objects here. Certain objects it doesn't work as well with, but for most objects this does. So I'm going to kind of close up this section by talking about some of our ongoing work with printed liquid metal circuits. So you saw Ravinder gave some really nice nice presentation on all the work that they're doing as well. And generally speaking, I mean, there's a lot of exciting progress on multi-material 3D printing of creating these highly elastic, mechanically robust soft electronic materials. And so this is kind of one of our recent attempts at that. And what we found especially promising are these so-called biphasic inks, where we blend the liquid metal with silver nanoparticles. And the advantage of that is that allows us to create basically a printable ink that we can print on ultra thin films like this tattoo, this temporary tattoo film. And again, using the same techniques that I showed you before, we can populate these circuits with surface mounted electronics and incorporate all sorts of different electronic and sensing functionalities in. As a bioelectronic interface, we found that these biphasic liquid metal silver inks are very effective in applications like ECG or EMG, so cardiac or muscle activity monitoring. And in fact, it outperforms or is comparable to or outperforms kind of gold standard bioelectronic interfaces using hydrogels or silver chloride gels. And the reason that it performs so well is because we can print these biphasic inks on these ultra thin temporary tattoo films. And here's just kind of another example of kind of printing these on a substrate. So I just want to kind of wrap up here by briefly talking about some of our work with conductive gels. I mean, Benjamin's already done a fantastic job covering this topic, so I'm not really going to spend too much time. Our kind of contributions here have been a little bit more niche in the sense that the ionic gels that have been developed until now are tremendously impactful for a lot of different applications in biointerfacing and sensing. And so what we found, though, is that for a certain class of applications, it does help to have hydrogel composites that are not just ionically conductive, but are electrically conductive. And the way we achieve that is through these percolating networks of silver flakes. I don't have too much time to kind of go into the enabling steps in the synthesis process to allow for getting these percolating networks with very low concentrations of silver flakes. But the point is that with our techniques, we can basically get fairly high conductivities, but still maintain the mechanical compliance of the hydrogel. And we found that that's been particularly effective in applications like neuromuscular electrical stimulation. So here we're basically using these gels as electrodes that we, in this case, say, place on the leg or on the forearm, and we can use these electrodes to deliver of electrical stimulation to the muscle to excite motion in the fingers or in the foot. And so what we found is because of that high electrical conductivity, we can deliver current and have basically muscle stimulation with these gels, something that we couldn't achieve with just using kind of more of a traditional ionic hydrogel. And then lastly, Benjamin did a really nice job showing self-healing hydrogel composites. And so I just want to acknowledge that work again on the top left. And building off of that work, we've also shown by suspending liquid metal droplets inside these composites, we can also achieve hydrogels that are electrically conductive, but also have this mechanical electrical self-healing property. So you can have basically hydrogels that you can kind of cut up and stick back together, and it's fairly robust. Okay, so I'm right at 30 minutes. I won't go through these conclusions. I just want to close by acknowledging again all the researchers and happy to take any questions.
Thank you, Carmel. Exciting, amazing work. We saw many different applications of these technologies, different types of devices, from wearables to robotics. If I might ask one question before we move to Sheila for the interest of time, maybe is
sorry, maybe I can also come with a question after yours. I think we have time for two, maybe.
Fantastic, yes, please. What do you see are the main challenges with liquid metal technologies? And exciting technology that allows a lot of stability. What do you think are the main challenges?
Right. So something that we're focused on right now is cytotoxicity of the liquid metal. So we found that for certain types of embodiments, and that the liquid metal is safe for interaction with biological tissue that doesn't interfere with cell growth. But in other cases, it does. And so that I would say that's the primary challenge, and that's kind of what we're dedicating a lot of our research right now to. A lot of the other issues I've been learning do deal with kind of manufacturability and also kind of reactivity with other types of metals. So these liquid metals cannot interface with aluminum; they'll corrode it. So that's another kind of concern or potential factor.
Yeah, thanks for that, and thanks for the fantastic talk. Really pleasure to hear that. And in a way, you possibly kind of answered my question at the very end of your presentation. So what I felt is that at all times we have to somehow link back to electronics. So you speak about these ICs that need to be integrated, and so there we have some rigid materials that always come in our way somehow because we want to create soft sensors. So I'm wondering, is there another way instead of using standard electronics? And maybe I think that you used the term silver hydrogels. Maybe that is a solution where we can create some new types of electronics?
I think so. I think a challenge is the stress concentration that you get when you have the rigid chip in contact with, say, your soft material. So having functionally graded materials where you have kind of a gradient in stiffness would really help with relieving those stress concentrations. So that's one. And something else I'm kind of excited, this came up in Ravinder's presentation, is also having just flexible IC chips. So maybe, can we create kind of CMOS architectures? We don't need that rigid packaging around it. And you can have that itself also be kind of flexible. It doesn't have to be necessarily stretchable, but flexible enough to interface with these softer materials.
Fantastic. Yeah. Thank you very much. Thanks a lot. And back to Panos. Thanks.
All right. Thank you.
Thank you. So now we can move to our last speaker for the day, Sheila Russo. She's an assistant professor in the Department of Mechanical Engineering in the Division of Material Science and Engineering at Boston University. And her work includes medical and surgical robotics and soft robotics and origami-inspired mechanics, sensing and actuation, and meso and microscale manufacturing techniques for this type of application. Thank you, Sheila, for being with us, and the floor is yours.
Thank you, Panos, for the introduction, and thanks Panos and Casper for the invitation to join this workshop. Just want to quickly say I'm really honored to be here with those amazing speakers. We had really fantastic talks today, really exciting work going on. So today I'm going to talk about soft robots for advanced interventional endoscopy, and I want to focus on, of course, some of the research that we have currently going on in my lab, the Material Robotics Lab at Boston University. We're working on the design, mechanics, materials, and manufacturing of soft multi-scale biomedical robotic systems. And in particular, of course, I'm going to focus on sensing applications for surgical robotics. Why is that important? And the motivation behind the research that we do, and the reason, the motivation behind the embedding, behind the need of embedding sensing technologies in soft surgical robots is what really gets us up in the morning and motivates us to be in the lab. And so if you're not familiar with what minimal invasive robotic surgery is, it's basically an advancement of procedures that are more sort of like traditional, like open surgery, where you would need to access the surgical target area by opening up the patient literally, so creating large cuts inside the body, and then at that point the surgeon would be able to navigate inside the body with their hands and see what is inside the body. So if they are targeting, for example, a specific tumor, they would be able to touch that tumor. And we know literature tells us that tumors typically tend to have, for example, higher stiffness than healthy tissue. And so the surgeon would be able to actually feel that kind of response as they are touching the tumor and see, of course. And so they are fully immersed inside that clinical environment. They have full feedback, both visual and haptic feedback. And they are fully in contact with a patient. But of course, those procedures present high trauma for the patient, longer recovery time as well, and higher costs for the hospital. So of course, we have seen a movement towards minimal invasive, less and less invasive surgical procedures, passing through laparoscopic surgery, where small tiny holes are performed on, for example, the patient abdomen, to perform surgical procedures by inflating the abdomen using carbon dioxide to create room for those surgical tools to operate. And then an endoscopic camera is inserted to see what is going on inside the abdomen as the surgeon is performing a surgical procedure. Now, both visual feedback and sensor feedback in this case are basically not anymore direct, but they are mediated from those through those surgical instruments that the surgeon is handling. And so there still is some sort of haptic feedback, but that is really much reduced. And moving on to endoscopic surgery, which is what we are really targeting, the kind of procedures that we are targeting in the research that we do in our lab, that is performed with flexible instruments that don't necessarily need to be inserted by cutting the patient or performing even tiny holes in the abdomen like laparoscopic surgery, but they are inserted through natural orifices, such as, for example, the mouth to navigate inside your stomach or your lungs, and so on. And so, of course, these procedures present less trauma for the patient, so lots of benefits. A lot of these procedures can be performed in a couple of hours or even less, and the patient can recover almost immediately and leave the hospital in the same day. But of course, there is a lot more complexity from the surgeon point of view. And what that means is that there are longer learning curves for surgeons to learn these procedures. Those endoscopes, those instruments are much more difficult to operate, and they present a lot of limitations. They are at this point really much the gold standard for diagnosis, but their therapeutic capabilities are still quite limited. And the reason is that endoscopes are great at navigating inside the body without, of course, performing cuts in the skin. But at the same time, they have poor instrument control. They just have a sort of like a joystick or a knob that controls cable-driven actuation at the tip of the endoscope. Depending on the kind of procedure that we are performing, endoscopes can have a couple or 1 degree of freedom, which is just bending of the tip of the tool. So there is definitely lack of distal dexterity of the instrument, and there is also lack of sensor feedback. So the surgeon is not able to basically feel the kind of forces that they are, for example, exerting on the stomach wall if they are passing the gastroscope through the mouth of the patient. They have to rely on visual feedback from the embedded camera that you see here on the endoscope, and LEDs that provide illumination inside the surgical target area. And so, of course, there is a necessary learning curve for the surgeon to map those visual cues to haptic feedback and information regarding the force that the instrument is applying. There is typically a working channel in endoscopes that provides the capability of passing through surgical tools such as forceps or graspers, and manipulate tissue, perform biopsies, or, for example, perform tissue removal in case that there is a tumor. But again, there are certain limitations when it comes to these procedures. And so that's where really our robotic systems are coming into play and sort of like tackle these challenges and perform procedures that are now difficult to perform, or even potentially in a few years, enable procedures that are not difficult to perform these days. Soft robots in this scenario present a variety of really exciting innovations and potential opportunities. Now, I don't have to tell you that, but this is, of course, a non-exhaustive slide. These are just some examples of soft robots that have been applied in medicine. And really, one of the main advantages, I would say, and what really gets the community excited to bring soft robots into the surgical scenario is the fact that soft robots are made out of soft, compliant materials. That means that they almost have the same sort of compliance as human skin, and so they are inherently safe for really close applications in close contact with the human body and with biological tissue, human organs, and so on and so forth. And so these are just a few examples. Of course, this is the CFLOP new project coordinated by Caspar, which was really a pioneer example of how a soft robotic manipulator could be applied in a variety of laparoscopic procedures to, in this case, for example, move organs. These are just balloons filled with water, I believe, that could simulate organs. And so safely, for example, retracting organs, which means moving an organ out from the scenario to access the surgical target area behind that organ. There are soft robotic catheters, various examples. This is a recent example from Shenhui Zhao at MIT of soft ferromagnetic continuum-like robots that can be miniaturized to be passed through vessels in the brain or in arteries. So miniaturization is definitely one of the most exciting new avenues for soft robots in surgery. And then, of course, again, a soft sleeve that can be wrapped around the heart to restore heart function. So again, you can see how soft robots can really tightly come into contact with our bodies and serve our physiological functions and enable better surgical procedures and so on and so forth. So in my lab, our approach is to bring soft robotics and surgical robotics together, really. And we are really targeting the mechanical side of this aspect. So we are really developing advanced manufacturing technologies to design, manufacture, and develop those platforms. And then we're really much talking to our clinical collaborators here in the Boston medical area to develop clinical solution viable surgical solutions to their approaches, and understanding where their limitations are, where on a daily basis they find that the technical skills that they have are limited for some reason, and where they would need a soft robot to solve those. And we are using an approach that combines soft materials with rigid materials, origami-inspired robotics to build those surgical robots, basically. And today I want to highlight two classes of soft surgical robots that we are working on, and those are hybrid soft foldable robots and soft reactive robotic skins. So hybrid soft foldable robots, as I said, are combining soft robotic technologies. So think about soft fluidic actuation, which is safe inside the human body because you can use, for example, water, saline solution, and together with origami-inspired rigid robotic mechanisms. And the fact that those two aspects are combined basically means that you can combine soft and rigid materials inside the body of the robot to make it in such a way that the robot can be folded down in small and compact configurations. And so, for example, it can be mounted around the periphery of a colonoscope, an endoscope, or pass through the working channel of an endoscope, or even mounted at a smaller scale outside a catheter, and then navigate and enable safe navigation inside the human body in that miniaturized folded configuration. And then once the surgeon has reached the surgical target area of interest, where, for example, a lesion or a tumor is, the robot can unfold and be deployed as a surgical target area and hopefully perform a surgical task that is of use to the surgeon, or enable a variety of surgical tasks. So these are just some examples of hybrid soft foldable robots that I've worked on in the past. And today, I'm mostly going to be focusing on this platform here, which is basically designed to enable to ease a procedure that is called endoscopic submucosal dissection, or ESD, which is a really technically difficult surgical procedure for early stage cancer removal in the gastrointestinal or GI tract. Typically, ESD is performed with traditional endoscopes, and through the working channel of those endoscopes, basically a tumor is marked by using a sort of like an electrocautery knife. And then around that mark, the surgeon is injecting with another tool, so swapping tools between inside the endoscope working channel, is injecting a saline solution to basically make sure that the lesion is better exposed. And once that is performed, the surgeon goes on to basically cut that tissue and remove the lesion entirely. Now, this procedure is really technically demanding because you have to switch continuously tools inside the working channel of the endoscope. That takes a long time. And also because there is risk of perforating the tissue, so perforating the colon, for example, as you are doing, for example, the cutting away of the lesion. And you have to be really technically skilled at performing this. There are only a few surgeons that are really able to do this nicely. And dexterity, again, is really limited because you have to pass all the tools inside the working channel, as I said, but also sensing is really limited. So you cannot really feel if you're perforating the tissue or if you are injecting too much saline solution and so on. And so we have created a soft foldable robotic arm that could enhance distal dexterity and sensor feedback in a procedure like this one. I'm going to talk a little bit about how we have manufactured the robotic arm, and especially the building bricks of that arm. So we are using a manufacturing process that involves soft lithography and laser precision micromachining, as well as chemical surface modification to bond together different materials, including soft materials and rigid materials. So we start with soft lithography, PDMS-like materials. We have done a little bit of research into a variety of different materials that are biocompatible for realizing these soft robots, and they are also more stretchable than PDMS, so they can basically actuate at lower pressures and perform larger deformations at relatively low pressures to build the actuation part of those robots. And so these are fully soft micro actuators, basically, that we then bond to rigid substrates, and those can be plastics, metals, whatever really you desire. We have focused on, once again, including into our manufacturing paradigm, biocompatible materials such that they can safely be used in surgical medical procedures. And so basically, our systems look like this, where you would bond a soft actuator here with that with a microchannel to provide fluidic actuation inside the actuator to a rigid substrate, which is in this case a fiber reinforced plastic. And then you continue sandwiching different layers of material depending on what kind of functions you want the robot to be able to achieve. And basically, at the end, you end up with soft foldable robotic actuators that look like this, and they are really thin, really can be miniaturized at really small sizes. We have gone through different levels of miniaturization from 1 millimeter, from a few millimeters down to 1 millimeter, with the idea being that, again, these can be passed through the working channels of current medical instrumentation or be mounted outside current medical instrumentation. And so we wanted to make sure that the size of our robotic systems would be compatible with those kinds of applications. And this is how they behave upon inflation, basically. You can tune basically how much the actuator would be able to expand, and we have seen that the fact that we are combining, we are sort of like creating hybrids between soft and rigid materials, actually, of course, enables a better performance of those soft micro robotic systems with respect to fully soft counterparts. And so you can tune the amount of force, for example, and torque that these robotic actuators can exert by engineering where the rigid components will be. You can tune the deflection of these systems and potentially better control their movement, or creating sort of like stop points inside the actuators to make sure that you are not, for example, actuating out of the workspace that you would require for a surgical procedure and potentially bump into tissue and cut tissue or perforate tissue and things like that. And you, of course, can tune also the stiffness of those robotic structures by, again, embedding materials in a smart way where they are needed for example, harder parts or softer parts, depending on the function that you want to achieve and the complexity that you want to achieve. But the cool thing about this is that you can embed sensing capabilities as well, because we are merging different materials in the manufacturing process. As I said, you can think about, for example, embedding conductive components. In this case, we have created a capacitive sensor by embedding conductive plates and conductive traces into this sort of like cage where the soft actuator is expanding. And so we are capable of monitoring, for example, the bending angle of this actuator, but we could, for example, use that as well for monitoring force interactions between the tip of the actuator and tissue and so on. And again, because these materials are integrated with a chemical surface modification process that enables integration of a variety of different materials, we can not only use copper in this case, which is what we have used, but also gold and other conductive materials that are compatible with our fabrication process. And the bonding between these materials and the soft elastomers that we are using is pretty strong for a variety of different cycles that we have tested. So going back to the application, the surgical application, we have we've gone to our clinical collaborator and spent some time in his lab and in the operative room and instrumented basically the tools that they were using to take some measurements regarding the workspace necessary to perform endoscopic submucosal dissection, as well as the forces that the surgeon is exerting as they are pulling tissue, for example. And with that kind of information, we were able to engineer our solution to this open problem, which is a DOF, multi-degree of freedom robotic arm, soft fold-up robotic arm with 3 degrees of freedom and an end effector that can grasp tissue and manipulate it. And so this is just an ex vivo test with a porcine stomach. So where we basically mounted the robotic arm around a colonoscope, a commercial colonoscope, and then we basically expand the structure, and with 2 degrees of freedom, pitch and yaw at the tip of the arm, we are capable of grasping the tissue and manipulate the tissue, which would enable, for example, tissue removal, biopsies, and these kinds of surgical tasks. The tissue is grasped using a miniaturized vacuum-based gripper, fully soft vacuum-based gripper. So switching gears to the second part of the talk, I want to just highlight the other class of soft surgical robots that we are working on, which is soft reactive skins. And in this case, again, the motivation behind that is, again, clinical, medical. We are collaborating with a surgeon at Brigham and Women's Hospital on improving colonoscopy procedures, safety in colonoscopy procedures, and ease of navigation. Now, basically, if you're not familiar with colonoscopy, colonoscopes, because they do not have, as I said, embedded sensing and then don't provide necessarily force feedback as the surgeon is navigating inside the colon, the surgeon can apply really high forces onto the colon tissue, which can cause perforation in postoperative complications. The fact that the patient is under anesthesia doesn't help either, because really there is no way that the patient could tell the surgeon if they're feeling too much pain, which could be an indication of the fact that they are pushing too hard onto this tissue. And so we engineered a solution where we have a sort of like a sleeve or a skin that can be wrapped around a colonoscope with embedded soft sensors and actuators that in case too much pressure is detected between the colonoscope and the colon, can deploy soft actuators that, if you will, look like sort of like an airbag that can basically distribute the pressure along a larger area in the colon, avoiding concentration of stresses, and at the same time provide us sort of like a cushion that can enable a safer and smoother navigation inside this unstructured environments. Again, these kinds of application in surgery, of course, are really exciting. But if you think about it, those unstructured environments that we have inside the human body, like for example in the colon, are really an example of what are the fundamental challenges that for us roboticists, what are the fundamental questions that we want to answer, right? And so navigating into unstructured and complex environments is definitely one of the most important challenges in robotics, as well as how do we integrate safe articulation and integrated sensing in a soft robotic system. What kind of materials are safe to use inside the body? What kind of sensing technologies are biocompatible inside the body? Then, of course, these kind of procedures restrict our freedom and somehow, because you cannot use really high temperatures inside the body. That wouldn't be safe, or really high currents could potentially cause harm. And so you have to think about that as you are designing and developing your robot. And so in this case, we have chosen soft sensors that are based on an optical technology. that are embedded inside our soft robotic sleeve. And with those sensors, once you press on them, they can automatically deploy soft robotic actuators to, again, distribute the pressure. We have worked to develop a graphic user interface that the surgeon can use, for example, from a tablet computer in UR to control the robot. And we have guided our design and manufacturing process with finite element analysis models, basically to make sure that the positioning of our soft optical sensors would be compatible with the application, that they would be able to sense the deformations and the forces that we wanted, as well as make sure that the system would lower the force concentration on the column as the system would contact the tissue. So we moved on to basically fabricating the soft robotic sleeve, and this is just based on casting and molding silicone elastomers, so pretty standard procedures. Again, the soft optical sensors that we have embedded in the sleeve are based on optical waveguides. Now, soft optical waveguides have been around for quite some time. They were first pioneered around the 90s by Professor George Whitesides. They are now used also in Professor Robert Shepard's lab for other soft robotics applications. And so these are created by basically embedding inside your soft robot soft materials that have different refractive indices, and such that they can guide light through your optical sensor. They are intentionally lossy with respect to a traditional rigid optical fiber. And in that way, basically, as the material is stretched or pressed onto, they can, the light that is transmitted through the soft optical sensor, of course, changes, and you can relate that to your inputs that you want to measure. So we have characterized our soft sensors. We have calibrated these sensors because, of course, by being embedded inside on top of the colonoscope, they can touch the tissue, the colon tissue, and respond to that. But at the same time, they will be bent together with a colonoscope. And for the sake of this application, we were mostly interested into mapping the forces rather than the bending or the shape of the colonoscope, but potentially you could do that as well. And so we calibrated these sensors with different forces and bending angle, making sure that we would create an algorithm that would map the forces that we were interested in. And for the sake of time, I will not go too much into the details of this, but if you're interested, there's a reference here to our recent article published in IEEE RAL. Again, we have characterized our actuators to make sure that they would match the expansion, the expansion required to contact the column walls. And this is a quick video where we validate the fact that our sensors are mostly responsive to forces rather than bending, and where we map the force that the system is capable of monitoring with respect to the force that our instrument testing machine is monitoring, and so pretty accurately. And then we tested the system in vitro. So this is basically a thermoplastic elastomer TPE sheet that we have used to simulate a colon, so a fake colon, if you will, for an in vitro test, where we basically show that a colonoscope is here pressing onto the tissue too hard, and then when we inflate our soft robotic sleeve, we are capable of distributing that pressure and continue navigation. And then in here, we basically wanted to quantitatively measure and demonstrate the capability of the system. And so at the beginning, again, the colonoscope is pushed, and we have a sensor reading of 4.7 Newton, for example, concentrated in one sensor location. The other two sensors are reading 0. And then once the sleeve senses that, it is capable of deploying the soft robotic actuators and distributing the force around the larger area, thus lowering, the overall stress concentration. So I just want to conclude here by again highlighting these two classes of soft surgical robots, hybrid soft foldable robots, and soft reactive robotic skins, and the sensing and the different manufacturing approaches to embed sensing capabilities, and why do we need sensing capabilities in surgical robotics and soft surgical robotics. And so the challenge is that as roboticists, we are facing for surgical applications such as safe navigation, again, distal articulation and integrated sensing, the lack of sensor feedback that we are presented with when it comes to applications like these. And so, but we also have to take into account a variety of different challenges when it comes to surgical procedures. Surgeons don't typically like to relearn. As I mentioned at the beginning, their learning curves are pretty steep, and so they don't typically want to relearn a procedure with a robot. And so it is important that soft robotics provides the capability of embedding systems such as these, where you can basically mount the robot on top of the traditional medical instrumentation, providing no disruption to current surgical workflow. And the fact that also the soft robotics is enabling novel approaches that are based on inexpensive materials, so creating robots that are disposable, single use, but at the same time can be built out of materials that are conformable, soft, safe, and biocompatible is definitely also an advantage. And I just wish to thank you for your attention, and thank you, of course, thank of course the members of my lab and our sponsors here. And I believe I'm almost out of time, so I will stop right there.
Fantastic. Thank you so much, Ila. Very interesting talk. Kaspar, is there anything you'd like?
Yeah, fantastic talk also from my side. Yeah, thanks for coming and presenting. I've very general question, because you could look kind of at two types of robots. One where you said that you want to go to a hybrid kind of solution, combining rigid components with soft materials. Well, your last system was probably fairly soft throughout. So where do you see the future in robotics, in particular in medical robotics, and also particularly in the context of being able to integrate sensors with these structures? Do you see it more in some kind of hybrid solution where we combine rigid components with soft ones, or is there a scope for totally soft robots in the future?
Yeah, absolutely. Thank you, Kaspar, for this interesting question. It's a really good question. So I forgot to mention that. So the first part of the talk where I talk about hybrid soft foldable robots versus the second part where they're fully soft, that is correct what you're saying, that the soft robotic sleeve is indeed fully soft, is basically mostly motivated by the scale of the robot. So in the application that I mentioned at the beginning of the talk, we were really interested in miniaturizing these systems as much as possible. And soft miniaturized robots tend to be really great for a variety of applications, but the amount of forces that they can generate is limited. And so the motivation, of creating those hybrid system is really because of that, because of trying to tackle that issue and solve the problem of enhancing the performance of these systems such that they can really be applied in surgical applications. So for the other robotic applications that I showed, instead, we were mostly working at a centimeter scale, and that is a lot easier. Like the forces that the sleeve is capable of generating are higher. So I believe in the future we will have soft surgical robots and soft rigid hybrids, robotic systems for surgery. I think it will be mostly motivated by the fact, what is the procedure that we will want to do? What is the problem that we will want to solve? And the idea of potentially having hybrids, I think whenever is needed, is definitely promising.
Thank you. Yeah, makes absolute sense. Panos, you have maybe a final question?
Yeah, I wanted to ask, there's a lot of attention for force sensing. But what other sensing modalities would be of value for the doctors? And maybe there are technologies, sensing technologies that you are experimenting with and developing in your lab.
It's a good question. There is a variety of different inputs, I think, that every surgeon would want to have specific for a surgical procedure. So yes, of course, there's for sensing, but also there is all the sensing that we should be integrating in the robot to, for example, map joint angle if we have a multi-articulated system and control the robot a little bit better. There's visual sensing and these sorts of things. Some other surgeons that I have collaborated with are really interested in, for example, bioimpedance measurements or bleeding detection and these sorts of things. And so it really varies depending on, if you want to focus on, the specific clinical application, all of them would potentially have different sensing inputs that would be of interest. There is different, and the fact that there is that variety of different sensing, different entities that would be needed to be sensed, also opens up interesting questions in terms of what kind of technology is best to be applied and what kind of manufacturing technology is best to be applied. We don't know that yet. And sometimes this is also caused by the fact that surgeons are not necessarily aware of the challenges because they are familiar with performing those procedures with no sensing or very limited sensing. And so it's I guess an ongoing talk that you have to have, an ongoing collaboration that you have to have with them to learn what their challenges are and present your possible innovations and really sit together and understand where the possibilities are.
Fantastic. Maybe we can also broaden a bit the discussion and include also Carmel and Benjamin, who are still with us. And maybe ask also their input and also yours, Sheila, about how do you see the future? What are the challenges that we still have to address? And what are the innovations needed? Or of course, for medical applications.
Okay, yeah, should I take that question?
Yeah.
Sure. So challenges for soft robots in surgical applications. Well, there's, I guess, a variety of them. It's a really good question. One is, of course, and has been brought up already by Casper before and Carmel, the interface between those rigid parts, hard parts, and soft parts. For example, in our case, we are, the last project that I presented, the soft robotic sleeve, we are using traditional LEDs for our optical sensing capabilities. And so if we really want a robot that is reliable enough for surgical applications, you have to think about, cycles of sterilization and potentially being able to perform really well such that we can go ahead and get FDA approval and all of those things. You really have to develop a robot that is really robust. And so that is a challenge. And it entails a lot of questions in manufacturing, but also materials and sensing technologies as well, which is really wide open, I think.
Carmel, would you like to add something?
Sure. I mean, I just want to echo what Sheila said. I thought she explained that very well. Something that I do get that does come up when I discuss soft robotics kind of in a medical context or kind of human is that robustness that Sheila's talking about, and also kind of having and this kind of builds on what Benjamin was saying, I've been covering on self-healing. Right, and kind of systems that if they do get damaged, that's the paradox of soft materials, right? Because they're soft, that also makes them very susceptible to damage and failure and poor mechanical load bearing. So I think having materials kind of more like natural materials that have this ability to kind of heal themselves or adapt their stiffness as needed is an important solution.
Yes, definitely. Self-healing techniques will be very critical. Benjamin, would you like to add something?
Sure. I think Sheila said a very nice presentation on the challenges integrating robotics in soft tissue such as the colon, and I think I think her strategies are very exciting, and I think that in the future, as we start to miniaturize electronics further, I think there's a lot of opportunities there by working with electrical engineering backgrounds to think about how we can sensorize and transmit data as opposed to just having the material do basic mechanical functions. I think those are quite exciting. I mean, if you think about it, there are pills now that can use chemistry to actually inject needles into the colon tissue, basically epithelial tissues, to actually have a better drug release properties or a more direct drug sort of injection without actually having to do any needle prick. So those are quite exciting technologies. They're already being commercialized. I think they've gotten a trial done. So there are, I think, opportunities really exist in the interface between several disciplines, and I think the workshop really highlights this aspect very well. Working closely with the electrical engineers to figure out how to miniaturize it, power the devices, and have sort of autonomous behavior. I think there's a lot of opportunities there, and certainly very challenging to achieve. But I think as a community, it'd be quite exciting to see how potential collaborations can emerge from such workshops.
Fantastic, thank you all. Kaspar, maybe some concluding.
I just reiterate something Sheila also said earlier. Despite the difficulties we have in communicating with surgeons or clinicians in general, I think that needs to be also continued. And again, that's why these workshops and the whole Hamilton Symposium is also is very, very useful. Because without the experts, the medical experts on board, it will be very difficult for us to develop the right system. So we might think, okay, we want to have the softest robot possible, but then in reality, that is maybe not what is needed. And here we need the feedback from surgeons. And I think that also, or clinicians, and that also applies to the sensing. Yeah? So what kind of sensing capabilities are actually useful for an operation? Yeah, I just wanted to add that point.
Fantastic. Thank you all so much for an amazing workshop. A lot of different technologies we saw today. And this is the end of the today's workshop. And I just want to highlight again that we have a virtual poster session. So please go to our website and view the posters submitted. And also tomorrow, session focusing on modeling, learning, control for soft robots. So one of the different aspects of soft robotic technologies for medical applications. And then this is the end of the workshop. And thank you all so much for joining us and also for these very interesting conversations and demonstration of various technologies.
Thanks again also from my side to the speakers, fantastic. And of course, thanks to the audience for coming and listening in. Thanks a lot. Have a good day.
Thank you.
Thank you. Thank you very much.
Bye.
Bye.
Bye-bye.